Okay, welcome everyone to CSE 132C Database System Implementation. My name is Arun Kumar. It's my pleasure to have Andy Pavlo visit us today. So Andy is a professor, associate professor at Carnegie Mellon University, and he's a well-known figure in the database systems world for all sorts of things. And he has been highly decorated with a lot of awards. It'll take me forever to go through all the awards, but he's also very well known for his fun stuff that he does in his talk. So I'm looking forward to what fun stuff he's going to do in today's talk. He started this company, OtterTune, based on his research and his graduate students and him. They've started this company. And I love the mascot. I love otters. They're so cute. So I love mascot. So thank you for visiting us, Andy. And just a announcement to the students, this talk is being recorded. I will announce when the recording will stop. And the recording will go on both the course Canvas page and on YouTube afterward. And in terms of protocol, Andy, would you want questions to be kept at the end till the end or during?
No, please, everyone, if you have questions, interrupt me, say who you are so I know your name, and then fire away anytime. Like, otherwise I'm just talking to myself for an hour and it sucks. Okay,
wonderful. So students, feel free to raise your hand. I will be monitoring the participants list and also put it on the chat, or feel free to unmute and speak. And I guess at the end, we will have a discussion after the talk, and that'll be off the record for the class. But until then, everything is on the record. So Andy, the floor is yours.
Hey, Arun, thanks for inviting me. I'll just say though, otters are cute. Those things are vicious as fuck, right? Those things are, you don't like, they're all cute and cuddly, but like they'll rip your head off. I can't say everything that they're known for to do, but like otters and seals don't get along. They don't like beavers either. Anyway, all right, guys, thanks for having me here. So today I'm gonna talk about, as Arun said, a project that we've been working on actually for several years now at Carnegie Mellon. And then we have recently spun off as a startup. And so I'm here to talk about sort of this, it's not a pitch about the startup, it's the core ideas about doing automated database tuning using machine learning, and some of the things we learned on the research side and having applied to in the real world. So the agenda for tonight is we're going to talk about the background of what knob tuning is for databases. We'll talk about what OtterTune actually does. And then we have two field studies of actually running OtterTune in real world scenarios and some of the things that we learned from those deployments. And then I'll finish up with talking about where we're going next with OtterTune. Like what is our big vision? All right, so a database knob, as I'm defining it, is a runtime control parameter that the database system exposes to you as a human administrator that allows you to change the behavior of some aspect of the internal system. Right, so the idea would be like you can set buffer pool sizes, caching policies, log file sizes. Right, they're knobs that allow you to tune the behavior of the system for your given application. And the reason why these knobs exist is because as the database system developer was building the system, at some point they had to make a decision about how much memory to allocate for a hash table, for example. And rather than putting a pound defined in the source code and assuming that there's some constant you can use for every possible application that ever would use the database, they instead expose it as the configuration knob, because they assume that some human's going to come along that's going to know exactly how the application is going to want to use the database, and therefore they'll be in a better position to tune that knob. But then, of course, the problem is if you have lots of these knobs, and there's sometimes latent or implicit dependencies between them, the setting one knob changes how you may want to set another knob. This is not feasible or just possible for a single human to be able to reason about how to set those knobs correctly, even though you can greatly improve performance and improve performance and increase the efficiency of the system if you can tune those knobs correctly. So even if you could do it for a single database, if you had enough time in your hands to actually do it, we see a lot of deployments in the real world where people are running hundreds or thousands of individual databases. And then now if you have to tune every single one, again, this is just not possible for humans to do. So to give you an idea how bad this problem is, this is a study that my PhD student did where she looked at the last 20-year release history of Postgres and MySQL, and she just counted for every new release how many knobs that they declared in their documentation. And so you see at the beginning of the century, MySQL and Postgres had under 100 knobs, and then over a 20-year period, MySQL increased by 7x and Postgres increased by 5x. Now, not all of these knobs are something you would tune to affect performance, right? Some of these knobs would be like file paths, port numbers, host names. They're things you wouldn't want a machine learning algorithm or any kind of tuning algorithm to change, because if you set them incorrectly, then the whole thing won't work. But there's enough of them that actually will affect performance. So what are people doing today? How do you actually want to tune your, how could you possibly tune your database? So you basically have 4 choices. So the first choice is that you try to do it yourself. We see a lot of this in sort of newer Silicon Valley style companies where there's like a DevOps role. And that usually just means that there's not a dedicated DBA. Instead, you have whatever person at the last job set up MySQL, Postgres, or the database at the previous company. They draw the short straw, and they're in charge of deploying the database on this for the new project and the new application. And again, these people are doing a bunch of other things, so they're primarily developers. So they're not going to know the internals of the database system. So what they end up doing is just Googling how to tune MySQL, how to tune Postgres. And you're going to find a bunch of these blog articles for every single database that's out there that give you some rough guidelines of how to set maybe 5, 6 knobs for your application to get better performance. So the problem with these blog articles are that they're not always correct. We found some cases where the things they recommend in these articles are actually, for some applications, the exact opposite of what you want to do. And they're only maybe suggesting how to tune 5 of them, or small handful of them, where there's a lot more that actually could affect performance. All right, so instead of doing it yourself, you could plunk down money and hire a DBA, hire a human expert to tune your database for you. Well, DBAs aren't cheap. So this is from the US government, the Bureau of Labor Statistics, for the average salary of a DBA in 2019 was $96,000 a year. Again, that's an average across the entire country. East Coast, West Coast, DBAs are definitely clocking 6 figures, right? And so you can hire one maybe to tune your database, but DBAs do a bunch of other things as well: query tuning, index tuning, backups, recovery, disaster management, things like that. So tuning might not be a high priority. And if you have hundreds or thousands of databases, you can't hire enough people to do this, right? So this is pretty cost prohibitive. All right, so now you want to get to more automated methods. The next approach is do rule-based tools. And so these would be these tools that have these heuristics built in that are written by human developers, where you punch in some basic information like how many cores you have, how much RAM you have, what your workload sort of looks like. And then they have these hard-coded rules that then spit out a recommendation for a small number of knobs as well. Every major database vendor provides these, like so IBM, Oracle, and Microsoft all have their own proprietary versions of tools that do these things. For Postgres and MySQL, there are some open source tools that are available. And again, at a high level, they all work the same way. So these are kind of like lowest common denominator tuning, right? Because it's not tuned specifically for how your application is using the database. It just says, hey, for hardware that looks like this, and maybe it's read heavy versus write heavy, try to maybe set some of these knobs. And so this will be better than the default you get when you call like apt-get install on Ubuntu. And it'll actually be better than what Amazon will give you on RDS. But even then, it's still not tailored specifically for the application running on the database. So what I'm going to argue for here today is the better approach is to rely on machine learning and take a black box optimization approach to tune these knobs for a database system for each individual application. And the idea, because we're using machine learning, there isn't a human required to make just hard decisions. The algorithms can sort of learn on their own how these knobs will affect the database system's performance, and it can come up with a customized configuration for any one database that ever sees. So this is what OtterTune is. OtterTune is a black box optimization approach for databases that specifically targets tuning the knobs. And so the idea is that we're going to train machine learning models that can automatically figure out how to set the values for these knobs based on how it sees the application using the database. And as I said in the beginning, or Arjun said earlier, this is based on research that I've been doing at CMU for several years now, and we've recently spun this out as a startup. So the current version of OtterTune supports Postgres, MySQL, and Oracle, and we're going to support databases running on AWS or on-prem. So It's always risky to do this in a talk. The live demonstration is rolling the dice. It didn't work on Tuesday when I gave this talk, but we can try again today. So what we're going to do is we're going to use OtterTune to tune a Postgres deployment on Amazon RDS. RDS is Amazon's database as a service offering. So instead of you like calling apt-get install Postgres yourself, you just click a button on Amazon and they give you, they give you the host name and port number for you to connect to the database. They manage everything for you. And so we're going to run the Tpcc Benchmark, which is a write-heavy transactional benchmark using our benchmarking framework on the database. And we're going to have two databases hooked up to OtterTune. The first will be one where we're going to actually do tuning. We're actually going to let the machine learning algorithms change the values for these knobs. And another one is going to be running the same workload. It's just we're not going to let it tune any of the knobs. And we'll use that as the baseline to see whether we're making things go better. All right, so let me. All right, I'm still sharing screen. You see this, right? Nope. All right, one sec. Sorry.
No, your slide screen is gone.
Yep, now you see this, right?
Yeah, we can see your demo screen. Yep.
Perfect, awesome. So let me make sure that I'm logged in. All right, so we have the monitoring database set up already. So we'll go through and am I in my kiosk mode? Why can't sorry, I not do this? I cannot minimize a notepad. That's a new one. Okay, whatever. We'll copy and paste this way. All right, so we're going to use again RDS. We're doing Postgres. So we punch in an identifier for the ID on Amazon that allows us to connect to this, and we'll give it the name TuningDB. And then we'll punch in this string. So there's a big step here I'm not showing where you basically have to go to Amazon and give us permission to be able to connect to the database. So one of the cool things that OtterTune, the way it works is we actually don't need to see the queries. We don't need to see the data. We can just look at these metrics, which I'll explain what they are in a second. And that's enough information to explain what the database is doing. So we can specify whether we want to monitor or whether we want to tune. For this one, we're going to do monitoring. And then we can specify whether we want to allow OtterTune to restart the database. So this will be an important concept as we go along. Some knobs in database systems don't take effect until you restart the database system. Now, Postgres has a bunch, MySQL has a bunch. There's no system that we've come across that doesn't have knobs that require a restart. The commercial guys like Oracle and so forth are a little bit better, but there's still some knobs that require a restart. So for this demonstration, we're not going to restart. We're going to let OtterTune tune the knobs that it thinks matters the most. And then we punch them some additional information into to the field. And then so now OtterTune can connect to the database and make sure that it can read everything that it needs to read, right? Again, this is just relying on the existing infrastructure that's available through Amazon and through the database system itself. So we're not installing any extra extensions to make this work. It's just using the standard SQL APIs or the standard AWS APIs to connect to the database. All right, so we've gone to Amazon. We've confirmed that we can connect to the database. So we have a new entry here. And we just go and check to see that we're actually it hasn't, give it a sec. Yeah, it's connected, but it hasn't pulled down the first database, the first configuration yet. But assume that it will, there it is. So, and then we can just see here, we see all the existing values for the knobs, right? So again, we'll let this run while we give the talk, and then we'll check at the end to see whether it actually makes a difference. Okay, so let me then switch back to.
So Andy, quick question.
Yes.
The service for tuning, the API for connecting it with the DBMS, is that a web-based thing? Is that a programmatic thing, or do you have multiple?
When you say, sorry, the API for connecting to AWS?
To the DBMS, to the installation that you're running. Do you do it as a generic service or like a REST API or something like that?
Like internally for our architecture?
Yeah.
Yeah, we have like a microservices architecture that allows us to there's a bunch of security things that we have to be very careful about because people are letting us connect to the database. So we sort of run things inside of containers, but then to actually connect to the database itself, you have to use basically JDBC, the standard connection library to connect to the database to retrieve internal like stats and other things. But then AWS provides a REST API to tune knobs and do other things like restart the database.
I see, got it. And then second question before you, maybe you'll talk about this later. Do you need telemetry data about the machine itself, or do you need only the statistics that the database catalog exports or something like that?
So I'll talk about that in a second. In some cases we found that you only need data from the database. In another field study we've done, we actually needed both because what they wanted us to optimize you don't know. The objective function we're trying to optimize can only come from like external services, like monitoring the OS.
I see. Got it. Okay.
All right, so let me share screen again. Screen 2. All right, you see that?
Yes, we can see your
awesome.
screen again.
Perfect. Okay. So while that's running, let me explain what Autotune is actually doing. So as sort of Arun was asking, like, how do we actually connect to the database? So you have to give us some permissions to connect to the database and retrieve these metrics and the current configuration. You feed that into the Autotune service. And then we have this driver running in Kubernetes that can connect to the database and get the current configuration, and then these runtime metrics from the system. So these runtime metrics are internal performance counters that every database system generates, like bytes read, bytes written, locks held, right? The names are different from one system to the next, but at a high level, every system's always generating these things or this data because they're meant for humans to be able to then decipher or understand performance issues in the system. So we retrieve all of that from the database. We then store this in our internal repository where we keep track of all the tuning sessions we've ever had for any database we've ever seen. And then our compute engine then trains a statistical model that can predict how the database system's performance will change or the objective function will change when we start changing the values for the knobs that we're tuning. So the objective function could be either the throughput, the latency, or another like CPU utilization if you care about other things, right? And then using these models, we do gradient descent and a recommendation algorithm to then identify some new values that we think will improve your objective function. We generate a new configuration, ship that over to our driver, who then applies the change to the database. If it requires a restart, then we restart. Otherwise, we just observe whether that made a difference. And there's a constant loop. We're keep feeding this data into our, keep retrieving new metrics from the system, training models on this, and then eventually we'll converge and produce a better configuration. So this is a evaluation that we published in SIGMOD a few years ago, where we compared how Autotune can tune either MySQL and Postgres against a bunch of different ways to tune a database. So the first method is using the default configuration you get from Ubuntu when you call app install. It's hard. It's always bad, right? Because it's very conservative in what kind of hardware it thinks you're running on. Like in case of MySQL, they assume you're running on a machine that has 128 megabytes of RAM, like some really low amount. Then the script or the rule-based tools I mentioned before, where you just punch in some basic hardware information and it spits out some new values. RDS is going to be what Amazon gives you when you install Postgres or MySQL through their hosted service. And then for DBAs, these are actually going to be humans, expert human DBAs who know that know each database very intimately and are able to come up with configurations on their own. And the last one will be Autotune. So the main takeaway from this graph is that Autotune using machine learning can either match or exceed what the human DBA is able to do. So in the case of MySQL, the DBA is the top MySQL DBA at Facebook, easily clocking a 7-figure a year salary because he saves so much money because they have so many MySQL databases. So that all the performance improvements he's able to achieve for them, at their scale matters a lot. And then for Postgres, it's the top DBA from Wisconsin Court System, which is surprisingly a big Postgres shop. So again, like the main thing here is Autotune is matching what humans can do without having to pay $1 million a year. Now, if you notice over here for MySQL, the human does slightly better than Autotune. And this is because there's a knob that turns off disk flushes to the log when transactions commit. And at Facebook, they were allowed to turn that off. Whereas in OtterTune, we actually put that knob on a deny list, because that, like, whether or not you flush your logs when transaction commit is the impact of that. If there's a crash, is an external cost that the algorithms can't reason about. So basically, if I don't flush my log, I tell the outside where my transaction is committed, but then I immediately crash, I may lose the last 5 milliseconds of data because it never got flushed to disk. And so whether or not your company or organization is okay with losing data like that is not something that OtterTune can learn on its own. It's an external cost. There's a human value judgment to be made there. So for that reason, we prevented OtterTune from turning off fsync. And then that's why the team is beating us. If we turn fsync back on, or sorry, if we turn fsync, let OtterTune turn fsync off, it'll learn that if you don't do disk writes, things go faster. So it'll end up matching what the human does. But again, the main takeaway here is, like, through machine learning, we can match what very expensive humans can do. So another study we've done where we compared tuning Postgres on RDS, and we can compare against what Amazon's going to give you by default again, but one of these tuning tools, in this case, it's pgtune, against OtterTune. And we're going to run the Tpcc workload on two different machine types or instance types on Amazon. And so in this case here, you see that for the M5 4x large, the OtterTune can get double the performance of what Amazon's going to give you by default. And again, Amazon's already tuned this for you. And a lot of people still run with the Amazon default, surprisingly. pgtune will get you slightly better, but OtterTune just crushes all of them. Now, if we run on a smaller machine, we see the same effect where OtterTune is getting double the performance, which is good. But the main thing to point out here is that on this smaller machine, the less expensive machine here, we're able to actually get the same performance as what you're getting on the more expensive machine. And so the cost difference is that this machine here, it costs twice as much as this one because it's a larger instance size and it's double the provision IOPS. So this is showing that, again, through machine learning, using machine learning to tune your database, you can either get better performance or you can get a lower cost depending on what you care about, right? So this is pretty exciting. So the original OtterTune paper was published in SIGMOD in 2017, which, as Arun could tell you, that's one of the top conferences in the database research field. When the paper came out, the other academics were like, "Oh, this seems kind of cool," but nobody in the industry really paid attention to it, right? It wasn't until I met the guy that runs all of Amazon's machine learning division. He came to CMU. I got 5 minutes of time to thank him for giving my student Dana for a couple $1,000s to run her experiments in EC2. And he was like, "Great, can you write a blog article for us? We just started a new Amazon AI blog and we need content." So we said, "Sure." And we just did a summary of what the SIGMOD article was about. And when this thing came out, then we started getting all sorts of these crazy emails from people saying, "This is the greatest thing ever. We had this exact problem. We'll give you money to fly a student out and come set up OtterTune for us to tune our databases." A bunch of people got really weird about this, about like, I'll give you money, we'll do a startup, and we'll make billions of dollars. My poor student didn't realize that these people are crazy and not to respond to them. I took a while to, I had to tell her, like, stop calling these people. It's not good for you. But the one email we got that was super interesting was from these guys here. They were from a major French bank and said, "Hey, look, we have this exact same problem. We're interested in actually, collaborating with you on the research side to maybe try to set up OtterTune, in their data center for their company." And so this is sort of the first sort of field study we've done where we actually took OtterTune outside the lab and tried to run on real databases and see what can happen. So, right, so for this first field study, like I said, the French bank reached out to us and they said, "Hey, we have 1,000 Postgres installations running in our data center in Paris. We want to use OtterTune to help optimize them and tune them." And we were like, "Great, OtterTune supports Postgres. We can do this." And so we didn't take any money from them. It was a research collaboration. So they took on a French master student on site and did an internship with them. We worked remotely to get them OtterTune up and running for them. And what was really interesting in the environment, it was sort of like with RDS where it's like self-provisioning. Internally, you go to their IT website, click a few buttons, and it would deploy a Postgres database. But then they had no idea whether people were actually tuning these things.
Andy,
so question? Sorry.
I have a question. So these folks, they just read your paper and then they pinged you?
No, it was the Amazon. They saw the
They read
Amazon
the
blog.
Amazon blog and then they pinged you.
Yeah.
Interesting. And so they were willing to work with you to give access to their database systems and their data. That is amazing. That is very rare. That doesn't happen that often. Enterprises don't reach and say, "Hey, come help us with our databases."
To be very, we talked about this afterwards. Like, they did not like. They're not obviously now to ship out any data. No, we couldn't see any of the queries. When Dana went on site with them, which is the next slide, she wasn't even allowed to touch a keyboard there. Like, so like the collaborator, like the guy working with us, she sat next to him and said, "Okay, type this," because he couldn't, like, she couldn't touch anything. Yes, banks are very, very, very strict and very paranoid about security for obvious reasons. We were able to make it work.
Got it. Okay. So another question I see on the chat, maybe we'll talk about this later. Question from Poonam: does
OtterTune use reinforcement learning? And how long does it take to tune a knob starting from the default to optimal value? The second question, sorry, the first question is the original OtterTune algorithm, which I'll get to, does not use reinforcement learning. We use Gaussian process models. We did implement for these guys there's a paper from Tencent and Xinhua from DLDB 2019 where they do deterministic policy gradients, actor-critic machine reinforcement learning. We actually didn't see a big difference in that over like the DNN or a deep neural network. But we can talk about that afterwards.
That's good. Let's continue.
Okay. So like I said, they had this big Postgres installation. They want us to tune it. So after the French intern got it working, they then started looking at those Postgres databases and see what we start doing. And so again, they originally told us they had 1,000. The real number was actually like 1, because it turns out what happened is the bank had this big initiative a few years ago where they said, we need to start using more open source software. And so that meant for every new project in your budget justification in the company, you had to specify what open source software you were using. So then the word got around the bank that if you just click the checkbox on the form and say, I'm going to use Postgres, it would spin up a Postgres instance, and they never had to put any data in it, never actually had run any queries on it. They never used it, and they just used Oracle and paid Oracle like they normally would. So they literally had 1,000 Postgres installations running in their data set in Paris that were completely idle, right? So that's not a paper I can write. You can't just say, hey, look, I ran a bash script to turn off 1,000 Postgres databases. That's not a paper. So they came back to us and said, okay, we're primarily an Oracle shop. Can you make OtterTune support Oracle? So we had a master student at Carnegie Mellon spend some time to port OtterTune to make it work for Oracle. Now, what's important here to understand is there's nothing in the machine learning algorithms that is database vendor specific. So there's no like algorithm you'd use for MySQL versus Postgres. It's what we had to change was the infrastructure to be able to connect to the database, retrieve the right information that we need, and then put it into a form that the models can then consume. That's the part that's database system specific. But once you do that, the algorithms don't care. The other thing I'll point out and say is we're not reusing data across different vendors. So I can't take data I've collected from Oracle and use it to tune a Postgres database. It just wouldn't work that way. But I can take data I've collected from one Oracle database, as long as it's the same version, and use that to tune another Oracle database that I've never seen before. So, all right, so then they said, all right, so they came back to us and said, okay, we were using Oracle. Can you make work in Oracle? We did that. Dana flew out to Paris in December 2019, right before the pandemic. Got on site, got it up and running for them, and we tried to see what happened. And so what was interesting about this is the target objective that they wanted to support was this thing called DB time, which I'm assuming if you're all undergrads, you don't know Oracle, so that's fine. It's a proprietary metric that Oracle uses. The Oracle DBAs use to determine whether things are running fast or slow. It's just sort of an amalgamation of a bunch of different wait times, versus like what I've shown so far is like latency and throughput, things that we normally as an application see. That's what we're trying to optimize. This is something internal to Oracle, and we want to see we could optimize this. So the setup for these guys was slightly different. Or it's slightly different than the next field study that we did. So I want to go through what happened. So rather than running on production, or the production database and tuning that, they made a snapshot of the database and set up a bunch of different cloned hardware in their data center, where we could run the database and run a workload repeatedly and not affect the live database. Meaning we could do all our tuning on the copies, and once we were satisfied that we found something that would achieve better performance, we could then promote that configuration up to the production database. And you have to do this because if you wanted to restart the database, you obviously don't want to restart the database if that's going to take down your application and people would see it and complain. So we were always running on clones. All right, so the first step of the driver, we would restart the database up and then immediately scrape the logs, the log files of the database system to make sure things were okay. I'll explain why in a few more slides. And then we would reload the database to a snapshot, and that would put us back to the same state we were when we made the copy on the production database. And then the next thing we would do is run an IO benchmark on the machine where the database system was running to. So we had SSH access to get to the machine and actually run scripts and other things, because it's just a VM running in their data center. The reason why we had to do this is because the database was using a shared disk architecture. So if you're familiar with like AWS, there's EBS or S3, right? That means that the storage is not actually physically attached to where the compute actually is for the database. It's on a remote device that you have to go to the network to connect. And so for these guys, the bank had this regulation where you can't have local attached storage. You can't write any of the database data to local attached storage. It always has to be put on the shared disk for auditing and security reasons. So they always knew what data was actually being written and where. But the problem was, this is running in their data center. It was really noisy because you don't control who else is writing to the disk or what other VMs running on the same box you are at the same time. So we would run these IO benchmarks to try to determine whether we were seeing better performance or worse performance because of the disk was running slow or because we were actually making things better. So these are results here from FIO, where we're comparing running a read-only workload on a local attached disk, like an M2 drive, or their shared disk architecture. And what you see is like there's a huge spike here where the IO of the disk write and disk read spikes by 3x. That's a lot. And so we needed this additional information in order to determine when our algorithms are making decisions and making recommendations for knobs. If we saw worse performance, we have a way to understand whether it's worse performance because the disk controller or the shared disk is acting up, or because they were actually bad values. So we didn't actually incorporate this data in our algorithms. It's more for us as humans to decipher what we were seeing, from the output generated by our algorithms. All right, so the next step is we then collect metrics from the system, and then we run the workload trace that we capture from the live system. Again, it's just the queries and transactions that the application actually executed on the production database, and we replay them over here. Oracle has really nice tools to do this. Like you just say, start the workload trace capture, and then when you're done, it stores it in a file. And then when you actually try to replay it, it tries to match the same parallelism or concurrency that you actually had on the production database. The open source systems, MySQL and Postgres, don't have nice tools like this. Then the next step, we would collect metrics again, and then compute a delta between what they were before and after. And we have to do this because some metrics are accumulators. They're just counting, how much data I'm always reading over time. So we subtract this from this, or this from this to determine how much data we actually read, or whatever the work we did when we actually ran the workload. We ship that over to Autotune along with the last configuration. We run our machine learning algorithm. It generates a new configuration that we then apply to the database and then repeat the process. So I'm going to show one graph here. One graph here of what we were able to achieve. So the x-axis is the number of iterations like that I just showed there, all those steps, and then repeat the process. That's one iteration. So load the database, run the micro benchmark, collect metrics, and then replay the workload. And so you see over here the human tuned configuration from the DBAs, and here's what Autotune is able to achieve. So in this example here for this database, we were able to improve the resource consumption by 50%. Now the amount of time here is about 3 days. So it took 3 days for the models to convert to find a new configuration. the time it takes depends on the complexity of the database system, depends on the complexity of the workload, and actually what the environment is. If the workload is really simple and it's a more simple machine or simple database system like MySQL, MySQL has way fewer knobs than like commercial Oracle does. So there's less things for Autotune actually to tune. In that case, we could probably tune that in less time.
Andy,
okay.
Question.
Yes.
The graph that you're showing, it seems like it's reaching the 2000 mark pretty soon. And you're pointing the best configuration to the right, but it's very comparable to the one on the left. So it's actually converging even sooner. How does Autotune determine when it's not going to be that much up? When is it going to decide that there's diminishing returns to keep tuning?
So in the commercial version of Autotune, we don't do this now. In the academic version, we would check the confidence interval. And if it was in some threshold, we said, okay, we think you've converged. There's other things you could do too if you identify that you converge, like maybe you tune 10 knobs first, and then if you converge, then start tuning 20 knobs. This was just trying to tune all 20 knobs at once.
I see.
Yeah.
Okay. So can the user of the database intervene and then say, okay, I'm pretty happy with what we've gotten here. It hasn't changed so far over the last few iterations, and then they can stop it, right?
Yes. Yes. There's nothing preventing you from doing that. Yes.
Okay. Sounds good. Thanks.
Yep. Okay. So what do we learn here from this deployment? So I can show the slide at the end. It's actually related to the question somebody had earlier about like, hey, did you try reinforcement learning? For this deployment at the French bank, we didn't see a major difference in the efficacy or the quality of the configurations generated from Gaussian process models to deep nets to deep reinforcement learning. Sometimes some perform better than others. Gaussian process models will converge more quickly than certainly deep reinforcement learning. But when the reinforcement learning algorithm converge, it's not like it produced always significantly better results. Sometimes it did, sometimes it didn't. So there's been another paper in EuroSys or EuroSys ML came out in April from the guys at IBM trying to tune FoundationDB. They basically found the same thing, that at this point it doesn't seem that the algorithm, it makes a big difference. Over time, who knows, if we start tuning even more knobs, it might make a difference. So I want to talk about some other things that we learned from this that aren't directly related to machine learning. And these are the kind of things you'd be mindful of when you're actually trying to build a tool that people want to use for the databases. There's other aspects you need to consider other than just like, hey, did I make things go faster, right? So the first thing was that, to no surprise, humans make mistakes. So part of the way we're getting a big benefit for the French bank is they had originally told us that they had already tuned the knobs for the database. And that was sort of partially true. What happened was they had tuned the database knobs when it was Oracle 11, but then they upgraded to Oracle 12 and they just didn't have time, or they forgot for this one particular database to then go back and maybe try to tune the knobs again, right? And so the obvious solution, in my opinion, is that the way to deal with this is we just need more automated checks and safeguards with something like Autotune or what other tools that are available to make sure that there aren't errors like this. So if Autotune was sort of running constantly on this database when they went from Oracle 11 to Oracle 12, in theory, it could have said, okay, well, I know that the environment has changed. Let me go ahead and start making sure I'm running with the most optimal configuration. All right, the next challenge you have to deal with is how to actually replay the workload. So again, the way it worked is you capture a workload trace of the queries and the transactions that they executed, the application executed on the production database. You then replay that over and over again on the clones so they don't interfere with the production database. And it's supposed to mimic how the application is using the database. So the goal was that we wanted the workload to be the same from one iteration to the next in terms of like the amount of queries you try to execute in each iteration, so that the metrics didn't wildly fluctuate. If I execute 1 million queries now and then one query in my next iteration, that looks a lot different. It's not the same workload. But the challenge is that sometimes if you give it a bad configuration, the replay is going to take a long time. So we would replay a 20-minute portion of the trace we've collected, and And we picked that time because sometimes if you picked a bad configuration, the replay would take hours and hours and hours. And you're basically getting useless data because you know the configuration is bad, but you're trying to replay the entire trace that you did before. So it's going to eat up all your time. So the way we handle that is we would identify that when if you're running twice as slow as you should, or if it's twice as long since you think you should be completing the workload trace, and you start running the workload trace, you have to go ahead and just kill that iteration, reset the configuration, and then go back to Autotune and get the next one to try out. But now the challenge is, how do you actually incorporate, how do you deal with these bad configurations? How do you incorporate feedback to your models and say, hey, we tried something and it didn't work, don't try it again. So there's actually 3 scenarios that can occur that you have to deal with for bad configurations. So the first one I've already talked about, a slow execution. I try some knob values that are suboptimal and it takes a long time and I have to go ahead and kill it. The next issue I mentioned when we scrape the logs, this occurs when you have a bad configuration and the system recognizes that when it starts up and it says, I can't deal with whatever you're trying to give me, I'm not going to boot, and it just crashes right away. If you set some knob with a negative value that it shouldn't be, it'll freak out at the very beginning and kill itself. And all we do is scrape the logs to try to identify when that occurs. The next one, though, is more tricky. And this is where there is an invalid knob value in the configuration, but the system doesn't actually hit an issue with it until some later point during execution. So like the system boots up, it checks some basic knobs, make sure that's okay, then it starts running. And then in the case of Oracle, like 5 minutes later, try to do something with one of the knobs that we set, and it would freak out and then crash, right? So there was some buffer size that we set it's not that we set it like a negative value. We obviously didn't do that, but it's when the summation of a bunch of different knobs together can't exceed the amount of memory that's available to the system, that it doesn't check until some later point, and then it freaks out and crashes. So again, when these 3 scenarios occur, we got to get feedback to our models and say, this is a bad configuration, don't try it again. All right, so how do we identify when there's a failure? Well, I've already started to say, like, we can scrape the log, look for explanations. You just do a grep and look for something that says bad configuration. And we would know that's something related to us that we try to do with Autotune versus some hardware failure or other issue. But how do we incorporate bad feedback for our models? For this one, we just set the objective function measurement for a given configuration to be whatever the worst configuration that we've ever seen before. And this is better than negative affinity because now you have a steep cliff in your solution space, solution curve, but it's bad enough where it's like it's not going to try it again. Now maybe like it may be around that region in the solution curve where you actually want to try it, and that's why again negative affinity would be a bad idea. But at least it's enough of a negative feedback to not try something again that would cause a problem. The machine learning literature says maybe try a 2x or 3x the worst value. We tried all of them and it didn't seem to make a difference. Okay, so this, like I said, the French bank field study was the previous year, and we have a paper published in VLDB that came out in March this year that describes the whole, what the whole process was and what we learned from it. So now for this next field study, a major travel website that you've heard of and probably have used reached out to us and said, hey, we're running a large MySQL fleet in our own data centers. We want to use Autotune to see if we can optimize performance and actually start doing machine consolidation, downgrade machines, turn off machines by having each node or each server in their workload do more than they're actually doing now. So this was a read-heavy workload doing log replay on the backend for the backend services. So this is not serving like the main website for the travel website. It's like for internal things that they use for analysis. So they already had sort of optimized configurations using Puppet scripts that had rules set up where it would look at what the amount of CPU and RAM that was available to the machine that before it deployed the database, and it would tune the knobs accordingly. And occasionally a human would come along and do some additional tuning as needed, but that part was ad hoc. So for this one, we're going to try to target 20 knobs. Actually, it's 23. The math is wrong, but it's going to be a combination of 19 dynamic knobs. Those are knobs in MySQL you can set without having to restart, and then 4 static knobs where you do have to restart. And again, they weren't trying to optimize performance for like P99 latency or throughput. They wanted to maintain the same latency that they were achieving now on the machines, but then they wanted to optimize other OS level metrics like CPU utilization or number of concurrent threads that MySQL gives you that. Basically, they want to see whether we can make it so that data was able to have more concurrent operations going on in the system without reducing your latency. And because that these are running in production, so we were only allowed to tune within the window where the DBA would be awake and on pager duty that could come fix things if we broke them. And we were only allowed to restart one time a day. So this is different than what I showed before in the French bank. The French bank was running offline on clones. This is actually running directly in production. But now the challenge is if you're not replaying a workload trace, how do you know whether you're making things better? Because it's not like the queries are always going to be different because it's based on whatever the application sends you. The database doesn't have control on that. So for this, what we did was we set up a tuning database that OtterTune was going to manage and optimize. And then we had a control database where it was running the same type of queries from the same application. It was in the same replica pool, but it wasn't running the exact same queries, right? Because again, the queries would show up and there would be a load balancer that would send queries to different replicas based on whether they're available or not. So we used this as to determine whether things were actually, we're making things better. It's not the exact same workload, but over time we would have enough data points to prove that yes, we're improving performance. So the first step, we're going to collect metrics from both the tuning database and the control database. And then this is the combination of database generated statistics from InnoDB and MySQL, as well as Telegraph connectors that retrieve OS level information. And then because there's no workload or no database snapshot to reinstall, we just waited for amount of time, like 10 minutes. And then we go back and collect the metrics again, compute the delta like we did before, and then ship the data over to OtterTune. It would generate a new configuration and go ahead and install it. And depending on whether or not this is this is our one shot for trying to restart the database per day, we would restart the database. So as I said, they want to optimize and reduce CPU utilization to show that we were actually able to do more on this machine. And so it worked so well in this first database here, we're able to keep, again, the latency is roughly the same at 1.4%, but the CPU utilization and the number of running threads was reduced significantly. And so in this particular workload, this read replica pool here, they had 25 nodes because they want to make sure they have enough capacity to serve all the queries they needed to handle. But if you now can reduce on a single box the CPU utilization by like 20%, and back of the envelope calculation says that's turning off at least one, maybe two machines. And at their scale with the number of pools that they have, and the number, potentially number of machines you can turn off, this is a pretty significant cost savings. In the second database here, we're seeing a huge reduction in performance, but not as a big reduction in latency. It made a reduction in latency, but not as big as reduction in CPU utilization and running threads. And this is because the number of queries that are arriving per second for this second pool were not as high as this one here. So this one was more overloaded, and we were able to cut down performance or improve performance quite a lot. All right, so what did we learn from this? Again, for this deployment, we were just using the deep neural network. We didn't try comparing reinforcement linear Gaussian process models. We did try GPR or Gaussian process models. We didn't really see a big difference in performance. Right? With enough data, they work about the same. So what are some other lessons we learned? So the first one we had to deal with was there are sometimes external costs or external factors in how companies and organizations tune their knobs. That's not something we can account for in our machine learning algorithms. So in the case of this deployment at the travel website, they had set the buffer pool size to be half the amount of memory that was available on the system, on the server. So the machine had 128 gigs of RAM. They set it to 64, whereas AutoTune recommended set it to like something 90, like around 90 gigs. So we went back to them and asked them, why are you guys artificially running with your buffer pool size so low? And they said because they only allocated half the memory to the database server in the buffer pool because they were concerned about some rogue application or some kind of flash mob effect where a bunch of queries are going to arrive all of a sudden, and the database system is going to start allocating a bunch of new connections which require memory, and they didn't want to not be able to have enough memory for those connections. So How often that occurs, we don't know, but that's why they artificially set their buffer pool low. So again, this is not something we would know just by looking at the data of the machine learning models. This is something a human has to tell us. So it's basically a UI UX issue where we now expose the ability to tell us what your value range not for certain knobs could be, because there might be a factor that we can't consider in our machine learning algorithms. All right, the next issue we sort of talked about before about system restarts. Again, some knobs don't take effect until you actually restart them. And of course, nobody wants to restart the database because the downtime can be quite significant. And if you're running in production, as these guys are, downtime means the application is potentially unavailable and people complain. Less of an issue if you're in the back end where it's like internal services where maybe people don't see, like, maybe the query fails and the application just retries it and it lands on another replica in a pool. But certainly if you're running a website where people are like trying to give you money to buy something, you don't want downtime. So people are very cautious about restarting in production. But the challenge is if they even let you restart, they kind of want to know how long it's going to take before the database comes back up. But there are some cases where, depending on what the knob currently is and what you set it to, the restart time can be non-deterministic. So the example I like to use is there's this knob that controls the log file size on disk in MySQL. So if it's currently 5 gigs and you set the knob to 10 gigs, when you restart and come back, MySQL says, oh, look, I was 5 gigs, but now I'm set to 10 gigs. I have plenty of space. I'm fine. I can come back right away. But if you go to 5 gigs and go from 5 gigs down to 1 gig, when you restart, MySQL says, okay, well, I got to get rid of 4 gigabytes of the logs so I can get back to my required file size. So it starts compacting. Depending on the speed of your disk, that might take a long time. So people don't like that, right? They want to know if I restart, I'm going to be back in a certain amount of time. All right. So the first question is, how do we know, how can the machine learning algorithms know whether it's allowed to restart the database system? Again, this is a human value judgment that we can't reason about. We have to be told. We have to be either told, here's the time range you're allowed to restart, and whether you're, how many times you may be allowed to restart per day. The next issue is how can you estimate how long it's going to take to restart? Well, this is obviously going to depend on a bunch of different factors, and we consider this an open problem that we don't have an answer to. It might just be training another machine learning model that says, my current configuration looks like this, my hardware looks like this. Here's how long I think it's going to take me to restart. But we just haven't done that work yet. All right, so what's next for Autotune? My PhD student Dana graduated in March or February this year. She turned in her thesis. She's now officially Dr. Dana. So she and I, and then another former master student of mine at Carnegie Mellon, have spun off OtterTune as a startup. And we had our launch a few weeks ago where we announced, like, hey, this is now a commercial product that's available outside the university. So the most surprising thing is that the number one requested database that we've gotten is Amazon Aurora. So if you don't know Aurora, it's Amazon's fork of MySQL and Postgres, where they've ripped out the storage layer and rewritten it to be optimized for a shared disk environment like EBS. It does a lot more than just writing to EBS. There's some concurrent transaction management down there. But this is the hottest thing on Amazon right now, and everybody wants us to tune it. Mariadb is a fork of MySQL. When Oracle bought Sun had bought MySQL in the mid 2000s. So when Oracle bought Sun, they now own MySQL, and so some of the original developers of MySQL forked it and made Mariadb. So it's some parts are still the same as MySQL. Some parts are different, but from our perspective in OtterTune, we think it looks the same. At least we can connect it the same way. So this is all fine, right? From a business perspective, yeah, we can tune more databases, we can tune more cloud systems. We'll get there. We'll do that. But to me, that's not good enough, right? That's not why I wake up every morning, right? Well, databases are why I wake up every morning, but I'm getting older. I need to get more thrills in my life. We need something else. We want OtterTune to be well known out in the world, not just for database tuning, but all sorts of other shit that we care about. So in addition to announcing the new commercial version 2 weeks ago, we've also announced that we now started a new record label for OtterTune. And we hope that this is going to be the premier outlet for database and auto-related hip-hop music or street music. So again, we have a startup doing all the database tuning optimization platform, all the machine learning stuff, all that's going on there. But then at the same time, there's also a record label where we're putting out music. So we in addition to the announcement, we have our first band. We've released first album, OKA. These are Otters out of New York City, and they're just like rapping over like dirty hip hop beats. So everything's available on Apple Music, Spotify, and Bandcamp. So if you're interested in this kind of stuff, go check it out. Okay, so what have I showed today? I've shown how we can use machine learning to solve what I think is a very important problem in databases, and that's doing knob tuning. It's not enough just to say I have great machine learning algorithms, or I'm going to use TensorFlow versus PyTorch. All of that sort of matters to some extent, but what we really found is that it's the infrastructure to be able to connect to the database and reason out what's going on and make sure that you're not causing problems, not making things worse for the database. All of that takes insight to understand what these knobs are actually doing, how the database system actually works, the things you guys have learned in a runs class. All that is necessary in order for you then to design the algorithms or the machine learning methods you need to go ahead and actually optimize them and tune them. So explain what I mean by that is, in order to determine what requires a human value judgment and what should be on the deny list for our service, you have to read the documentation and understand, oh, it's saying it's doing this. Yeah, that's going to cause a problem. Here's why. We don't let Autotune tune that, right? And so I think I also showed you today is that Autotune is able to tune we can improve performance. Oh.
Andy, your database is now optimized and ready to use.
Sorry, I always forget that. Yeah, so let's finish up and go to the demo. All right, so let me bring it over here. Right, so where we left off, again, we have our, I'm probably going to restart. Yeah, that's why. Every time I always forget that, sorry. Boom, right, so we have our database. This is the one that we're tuning. And based on the default, we're able to get 70% improvement. And then we can go see, here's all the configurations. Maybe I need to, there we go. I can go here and see what is actually, what it actually modified, how things changed. And maybe I can do a comparison against the first configuration. And it just shows you, what the values were before and after, right? So, okay, so against ourselves, we were able to make this database run 70% faster. And just prove that this is actually running for real. We can then come to our chart. We can add in our monitoring database. Again, this is running the same workload. It's just we're not tuning at all. And you can see at the very beginning, I mean, roughly, it's a little higher, but roughly about the same performance. But over time, it's about over 2x performance improvement. And again, this is all through machine learning. We didn't actually have to tell anything about, hey, if you tune these knobs, it's going to affect performance this way, or one knob is going to affect another knob a certain way, right? As long as they're allowed to be tuned by machine learning algorithms, we don't know and don't really care what values they're actually going to get set to, and the algorithms just figure it all out on the run. Okay. All right. Cool. So with that, I'm happy to answer any questions.
Okay, great. Thank you, Andy, for the lovely talk and the demo. Let's give Andy a round of applause. The reactions work. They don't, unfortunately, so I'm just going to clap for you.
Yeah, you're enough. That's fine.
The students do too. So I do have a bunch of questions, but let's open the floor to the audience. Students, do you have any questions? Feel free to raise your hand or put this on the chat. Okay, so
it could be about OtterTune, about data in general, whatever you guys want.
Okay, so I can probably get started with the questions then. So the first question I have for you, the metrics that you showed, the throughput metrics or aggregate metrics, have you looked into issues of robustness for different kinds of queries? So if you remember, one of the questions Surajit asked for ML for database system work was, cloud vendors, they like to give SLAs, and when different kinds of queries are executed on the system, do you see different queries responding differently to the newly configured settings or something like that? Like, what if I run a query today that suddenly tomorrow it takes more time or dramatically less time? What do people think about that?
So we actually, We haven't measured that. We purposely designed AutoTune not to have to look at queries or the database itself, because that brings a bunch of security concerns in, right? People, people are giving you access to touch the database. We have to do it in a way where we can't actually see any queries or any user data, because even the queries themselves would leak things, right? In Postgres, there's a way to turn on, there's an extension you can turn on called PG stat statements that keeps track of histograms of queries. That we have not analyzed. So I don't know the answer yet. In the case of the travel website, for example, we made sure like the P99 looked the same. So in that environment, the queries were somewhat homogeneous, meaning it wasn't varying widely from one day to the next, and our P99 bounds were pretty tight. So we were quite satisfied with that. To your point, I agree with you. Over time, I'm sure at some point we'll see somebody who has a workload where things go terrible for certain queries. We just haven't seen that yet. I need more data.
Got it. And if they are concerned about it, I'm sure they will tell you that.
Yes, of course, yes. You'd be surprised that some people really have no idea what's going on. Right. They're like, yeah, queries are running slow. We don't know why. Are you disk bound or are you CPU bound? We don't know. Databases are complex pieces of software. There's a reason why, think about this. I always say this in my classes. Think about other types of software that are widely used, like a web browser or whatever. Yeah, web browser is a good example. Everyone uses them. They're super important. But I'm pretty sure UCSD doesn't teach a class on how to build a web browser, right? But Arun's teaching class on how to build a database system. They're that important. They underpin almost every aspect of our lives, and they're complex pieces of software, and that just the average person is not going to know what's going on. So this is why I'm a big proponent of using methods like this. Now, I'm sure someone somewhere is going to have a problem where AutoTune makes one query go slow, and then we'll have to figure it out. But we're not there yet.
Okay. Yeah, that makes sense. I think they're starting out with something that gives them this sort of 100% jumps and stuff like that. They're not going to be impressed. So at some point you might end up with a Pareto trade-off of some sort. Okay, so I have some questions on the chat from Shardo. Shardo, would you like to unmute and speak, or shall I just read out the question?
Yeah, hi. Great talk, Andy. So just wanted to know, during the initial phases of the model development, how did you collect the data and how did you select the best model out of all the models available?
So in the very first version of AutoTune back in the university, we teamed up with a machine learning professor, and he was really big on Gaussian process models. So and that's what he wanted to use. I said, okay, sure, that's fine, let's use that. I have no strong opinions on the machine learning side of things. That's not my area of expertise. I'm not trying to write ICML NeurIPS papers. Whatever you got, I'll take it, right? So that's why we picked Gaussian process models. And then we tried extending them to use contextual bandits. That one we didn't see a big difference. And part of the reason actually we decided to do the deployment at the French bank, which is risky to do. It's hard, right? Because it's you're going down this path. You're not sure it's going to turn into paper, because it might just be negative results. Oh yeah, machine learning doesn't make a difference, right? As part of that deployment, we then implemented the reinforcement learning and the deep neural network, just so that we could do an additional analysis if it turned out that the results were not as promising or didn't turn out the way they did. And like I said, we didn't see a big difference in performance. Big difference in the efficacy of the algorithms. So then I think your question was, how do we collect the original data in the beginning to train our models? So on the academic project, we actually just did a parameter sweep of all different variations of the way to configure Tpcc and YCSB and a bunch of other open source benchmarks. We just collected everything, and then we used that as sort of the starting point to understand what was going on. It's hard in academia getting access to real world workloads. That's not an easy thing to do.
Yeah.
Okay. Thanks, Shardo. Next question from Aaron. I can read it out. Unless Aaron, do you want to speak? I guess not. So I can read it out. So Aaron asks, how do you utilize Kubernetes and microservices in your tech stack? Do you just spin up a pod deployment for each instance that you tune? How do you also maintain such clusters?
Yeah, I got it. So for those of you who haven't built I've never built like a cloud-based microservice before, because I care about building a database system itself. So like we don't run, and we're not trying to run major deployments at the university for these things. So one of our first hires is actually a former student of mine from Carnegie Mellon, and he was at Uber, he was at Google. He came and said, "This is how we're going to organize everything." We spin up a separate pod per database instance, and we do that for security reasons. So that way, if that pod somehow gets compromised, it can't connect to another database. The amount of work that the driver is actually doing in that pod is very light, because it's just basically a conduit to get data in and out from the database system we're tuning to our service. And then, so I think your question was, how are we actually running Kubernetes? We're using Amazon's hosted Kubernetes service. So that's the thing you quickly learn about when you go in the real world. Like, yeah, it's all this shit's open source. You can set up and run it yourself. Amazon makes it so easy and so cheap, at least in the beginning, just to click a few buttons and they'll take care of Kubernetes for you, right? Because like developers are expensive. Rather than paying somebody $100 an hour to spend 100 hours to figure out how to get Kubernetes running and maintain it, I pay Amazon whatever $20 a month to do it for me. So how Kubernetes works, I don't care. What are they doing to make sure it's safe? They're doing that. And that it's nice because I can focus on the things that I care about, or things that actually contribute to to my project, what I'm trying to do. I focus on the database tuning stuff. That same argument can be made for for database systems. Like all you guys here they now know how to build your own database system. You're gonna go out in the real world, and oftentimes at these companies, they're like, hey, MySQL sucks, Postgres sucks, let's build our own database system. That might not be the right thing to do, because building a database system correctly is hard, and it's not maybe contributing to the what your organization is trying to achieve, or the business is trying to achieve. So when possible, let other experts figure things out for you, within reason, of course.
That sounds good. Although students, I would say this class is also useful if you go and join these very cloud vendors. You can go work for Aurora and Redshift and Oracle and all of these people, yes. And they can improve their systems too. And you can also apply it to data science and machine learning systems. You don't have to build another RDBMS.
Yes, I would say also, I imagine your students are like my students. The database companies can't hire them fast enough. Like we're sort of in the golden era of database systems now, where there's a ton of them. Postgres is getting very, very good. There's a lot of systems that are very, very good, but there's still a ton of startups still coming out today that are trying to improve on these things. So if you can build a database system, you're in demand.
Definitely. So related to that, Andy, I have a question about the future of cloud. And the future of cloud is serverless and disaggregation and all of that stuff. Database systems are also evolving with tiered caching and all of these things. So how do you see knob tuning evolving in that landscape? It's not just an installed machine on a provisioned instance, but now you have elasticity, you have resource disaggregation. What does the future look like in this space?
Specifically for knob tuning, again, the algorithms don't care, right? Like, we don't know whether we're tuning, the Linux kernel parameters, which we've done. I can share those slides. Or we're tuning a database system, right? It's just numbers in, numbers out. The infrastructure around it is what sort of matters, right? So this is a quick study that I did. Why is this bar in the problem? Sorry. Way to get rid of this. Sorry. No, that didn't do it. Sorry, whatever. Like I had a master student extend OtterTune to support tuning the kernel parameters, because for Postgres that matters. And the way we sort of handle that was just we take all the Linux kernel parameter names, and we just append Linux and in front of the string, and threw that at OtterTune. It's like, oh, it's a database knob, I'll tune it. And we just knew on our driver's side to say, oh, it's a kernel parameter versus a database system parameter. And so here, it's just showing you here that it works. That if you tune the data system plus the operating system using the same models, it can make a difference. So now to Arun's question, like, think now of this, like you have all these different services. If you can either optimize them individually, or if there's a larger APM or a larger metric that you're trying to achieve across all these different layers, as long as you're able to collect that information, collect that metric, and provide it to a tuning service like Autotune, and then expose the APIs that allow Autotune to change the configuration for these different services. It doesn't matter whether it's a single node or a crazy broken up microservice architecture. It's just trying to optimize the same thing. Now, the more knobs you throw at us, the more data you throw at us, certainly that takes longer for the models to converge. So it's not like you just throw anything at us and a machine learning algorithm to solve it. But I foresee potentially in the future, you could have something that looked at the full stack and try to tune those. We've been asked this. So the Linux kernel parameters come up. We also asked to tune the JVM a lot. One guy came to me after our talk, said, I have 100,000 JVMs running and we need to tune them and we don't know how to do it. So again, in theory, Autotune can do it. We just, my first love is databases. I guess my first love is my wife, second is databases, but like, that's what I'm focused on at the moment.
Yeah, who wants to tune JVMs, right?
Yeah.
Okay.
Now, Twitter did this. There's a blog article where Twitter bought some startup as an acqui-hire kind of thing, and then they had those guys try to tune the JVM, and it made a difference for them.
Okay, sounds good. Sounds exciting. I mean, it seems like this sort of generic architecture that can interface with the system in this well-defined manner can keep up with the evolution of the system architectures themselves. Okay, so we have some more questions on the chat. One from Jerry, I hope I'm pronouncing your name right. Will these parameters affect how the query compiler generates query plans? If so, will database system developers need to consider integrating Autotune with their database? It goes against your decoupled architecture, I guess.
So there are some knobs in some databases that will affect how the query, what the optimizer, the query optimizer, query compiler. You're presumably you're teaching from the Cal book, right? So that's why it's query compiler.
Sorry. Hi, Andy. Yes, I'm like for OLAP. I'm meaning for OLAP compiler, the query compiler. Since the query plan for like the optimizer generating query plan is really important for OLAP system.
Correct. So sorry, I just the comment I was making is that in my class I don't say query compiler, I say query optimizer. But there's a textbook from Wisconsin that Arun got his PhD. That I think the textbook says, I don't have it here, do I? That says instead of saying optimizer, it's a compiler. So it was a side comment. Sorry.
No, we call it both. We call it query processing and query optimization. I don't actually call it query compiler.
Okay. So there are some knobs like in Postgres that can affect some aspects of the query optimizer, the query compiler. Like you can change like what it thinks the effective cache size is going to be, or like the relative cost of a sequential scan IO versus a random IO. So yeah, we tune those knobs as well. And so Autotune can handle them. They do make a difference. But then your larger question is like, does the database system developers need to consider like, should they directly integrate something aspect of their system into to Autotune? I'm arguing no, because one, it's a lot of work. Two, you don't want to assume that somebody is always going to be running something like Autotune, right? And it's something where I think it's just more complexity in the system that may be unnecessary for a certain number of people. And so we only use the standard APIs that the data system is exposed to us. So now they're specific to each database. Like the query to go get the current metrics from Postgres is different than the query against MySQL and Oracle. But that part, we write once in our service and we're done. I don't think there should be. We don't require additional hooks in the data system to, that based on assuming I'm running I'm using something like Autotune. I have another line of research though, where it's instead of taking a black box approach, we take a white box approach and say, if you design the database system from scratch to assume that it's going to be controlled by autonomous components, what would that architecture look like? And that's a whole another talk. Arun will invite my PhD student to come do that at some point. That's another system we're building called Noise Page. And again, the idea is that as we're building the system, instead of saying, hey, let's do X, let's build our feature this way because that's going to make things so much faster. Instead, we say, can we build X? Can we build that feature in a way that can then be more easily observed and optimized by machine learning algorithms? So Autotune is like taking existing systems. Noise Page is taking a system you built from scratch. That's a whole another topic.
Thanks a lot. Yeah, I'm a fan of your database course, and I finished the Bathtub DB, and I wonder, is there some open source DB you recommend to learn if I want to get more experience?
You hang out Arun, right? Like he's a top researcher at UCSD.
Yeah, I asked the Professor Arun in winter. There's no positions at that time, so I'm sorry.
Systems researcher here in the database area, Andy. My lab is pretty oversubscribed. So in terms of opportunities, Jeremy, I think internships are also a good opportunity. Like there are
I will join a database company after graduation this summer. So, but I want to keep learning.
Send me an email, and we'll figure out something for you. Okay.
Thank you. Thank you.
Yep.
So we have a couple more questions, and then we can wrap this up. Poonam asks, how does Autotune decide between hundreds of knobs and thousands of metrics? Which ones to train the model?
Yeah, so for the metrics, we take them all. Well, no, actually, I take that back. I don't have slides on this. So for metrics, the challenge is a bunch of them are redundant. So in MySQL, there's a metric that keeps track of like bytes read, and there's another metric that says pages read from disk. And it's the same. It's measuring the same thing, just in different units of measurement, pages versus bytes. So we run a clustering algorithm, just I think k-means or dbscan, I forget the exact one, that identify groups of metrics that always seem to be going in unison with each other. And then we pick the one, the center, that is represented for all of them. So we do that. For knobs, the academic version of Autotune would run a lasso-based regression to identify the importance of knobs affecting the objective function. So the idea is it would give you a ranking, say, we think this knob is going to affect performance the most. And therefore, depending on how quickly you want to tune, like if you wouldn't say, I'll give it 3 days, it'll take 40, 50 knobs. But if I only have maybe a couple hours, maybe I'll just tune 10 knobs. So there's that sort of choice that's been made. That doesn't exist yet in the commercial version, but it's something we'll eventually add. And the original, again, the Sigma paper that's available on my website or the Autotune website will describe these algorithms.
Okay, great. So last question, and then I will stop the recording. From Tara, were any of the database configs ultimately chosen by Autotune unusual? That is, where the configs that a rule-based approach or a human expert would be unlikely to choose. That also reminds me of the Google DeepMind data center configuration tuning thing, where they said civil engineers and mechanical engineers would not have picked this or whatever. What do you think about this?
Yeah, that's a good question. I actually don't know. Well, so I would say I think I said this example in the beginning. We've seen, this is a tweet or I don't know if this is a paper or a blog article. We've seen when we first started the Autotune project to figure out, okay, what are we up against? How are people tuning databases now? We go look a bunch of blog articles of like that I showed in the beginning of like, hey, here's the top five rules or top 5 knobs you should be tuning in your database. Number 4 is gonna blow your mind, right? Some of them are actually incorrect. So an example would be at the book, cut that out. Sorry, at the travel website, there's a knob in MySQL called InnoDB Adaptive Hash Index. It's on by default. A bunch of the blog articles say, yeah, keep that on. That's going to help you. For that first application where I showed, a huge reduction in CPU usage, you actually want to turn that off. For that particular application, for whatever it is that the queries are actually doing against the database, we don't know because we can't see them. It's a 30% performance difference if you leave that knob turned on. So Autotune says turn that off. So that's an example where humans are going to say do this. Our algorithms found found the opposite. So what I want to do is somehow like, I'm not, publicly shame them. You can imagine like, hey, here's all these different blog articles. People say how to tune, MySQL Postgres, and then we take what they recommend and compare it against what OtterTune says and show how they're wrong. And then we can rank who's the most, who's the best DBA or something like that, right? So that's something, I think that MySQL one's a good example of this.
So related to that, Andy, is there a notion of explanations that these database users want from Autotune? Like you say, here's a new config and it's improved this. Do they want to know why it improved it, or some explanation for why the knob was tuned this way versus that way?
The more sophisticated users, yes, do want this.
Okay.
But so at the travel website at the French bank, they had very expensive full-time DBAs that are experts in MySQL and experts in MySQL and Oracle. We've talked to a lot of people where, like, again, they're DevOps. They just don't have the in-house expertise. So they come to us because we know something about databases, and so they're starting trusting us. Now, at some point, yes, we'd want to be able to say, to have some kind of explanation, and to what level the sophistication of what that explanation is can depend, right? So you can imagine something really simple, like if you can identify that like the workload's read heavy or insert heavy or update heavy, you could then say, okay, we set the knobs these way because your workload is read heavy, and in 95% of the read heavy workloads we've tuned before for MySQL version, whatever you're on, these things help. Or we can start maybe tuning only one of the knob or a small subset of the knobs and show that, like, okay, this is where you may be getting the majority of the benefit you're getting. And then like that gives you like 95% of the improvement, and then the remaining 5% is from remaining knobs. Something like that we could consider exposing to the website. We just haven't, we're not looking into it just yet.
Sounds good. So let's thank Andy again. I just wanted to show, here's my favorite plush toy. It's a gift from my spouse.
Nice.
So,
otters are vicious as fuck.
They're vicious. They are also cute. Oh. So it's a good gift for us.
So in Singapore, there's actually gangs of otters. I'll send you the link afterwards. You send it to the class. There's gang of otters, and they have turf wars where they'll fight each other.
Wow.
They're vicious.
Okay. Well, Andy's pretty vicious with his research too.
No. I'm pussycat. It's fine. All right, so what happens next? You go off the books and do more questions, or what happens next?
I think we can stop the recording here, and then we can have some off-the-record questions from the students if you want. So thank you again for visiting us, Andy. And thank you.
Thanks for having me. It's awesome.
Take care.